Hello, everyone. Thanks, Dale. Thanks, Matt, for reading the presentation. I am a structural engineer, and today I'm hoping to talk about a bit in more detail, basically echoing what Matt and Dale have been talking about in the the off-site construction, and focusing on, as a structural engineer, how do I actually play a part into the whole system to collaborate with fabricators to people on site. And Everton Football Stadium is a project case study that we're going to go through, and I'm really going to go through kind of the process of how we play a part in it. Next page. Yep. So a bit about the project. It's the new football stadium for Everton Football Club. It's located in Liverpool in the historic Bramley-Moore Dock, which has a complexity by its own because it's actually a dock that we filled in completely, and that's why at the bottom you see, oh, not quite there, sorry. Let me just go through the people involved. So we got BDP, Patterns, and Maze as the architects, Planet, we got Laing O'Rourke as the main contractor, and then finally Buro Happold, and we pretty much took on most of the engineering side of things, and I'm in the structure team. Some good news about the football stadium in the new Premier League season, which is happening soon. They've already moved in, and they're going to start playing football in the new ground, and it delivers on time and on budget, which is always nice to see. Cool. So a little bit about the projects I've mentioned is a dock area. It's all filled in. That's why we've got nearly 3,000 piles. And the whole thing is supported in suspended ground as well. That's because we expect the soil to settle, which is unfortunate. We can't take the capacity of that, but it's just what the site is limited to. In the middle bit, you see the stands for this football stadium. You notice, hopefully you can, kind of in the east and west stand, those are the concrete frame, and the rest of them are steel frame. And I think it's an obvious question to ask why. Why the splits? Why do we do it that way? And that's because Laing O'Rourke, as the main contractor, have been engaged at a very early on with the design team. And this is actually based on their manufacturing capability and also their construction sequence and schedules to make that decision together as a whole team from an early stage. The roof used is quite a funky, curvy roof, and everything is done through a computational approach. So from the start of the project, from the RIBA stage 2, everything is modeled parametrically using Grasshopper and also using BOM, which is the Buro Happold internal developed software. It's open sourced. So it the parametric model become the central of truth of how the geometry looks like, and that's pushed into analysis models, into our Revit models, and that really allows us to change the shape and work with the architects and the contractor to actually change it to facilitate what's best for everyone collaboratively. So a lot of precast as well. So the mention of off-site construction, that's very true for Everton. I think that entire thing is pretty much off-site construction using precast elements. Very rarely, there's only like the foundations that is actually in situ concrete. And I'll go into more detail later on of how do we actually, as the structural engineer designer, get into that kind of ecosystem and collaborate with the fabricator on that. Finally, I want to touch on the 3D detailing. Not only is the model 3D modeled, every single nuts and bolts, like going back on the last presentation, is modeled in 3D. And even the fabricators all work in 3D into the machine, and on site they use iPad to look at the rebars to actually assemble them, rather than 2D drawings where some things might get confusing in terms of how the rebar fits. Drawings, I'm not going to go through all the points, but it's just to show you kind of the amount of information that is embedded in our design data. And one driving force there is that we're not only just designing a normal building, say for in situ typical detail for how the wall looks like, we're actually designing to how the precast elements would look like and how would that fit into on-site when they pour the in situ concrete inside of it, and producing details that is relevant to it as well. Also mentioned about health and safety, that has actually info. You can kind of see the little triangles there. There are just so many health and safety info, especially things that actually from understanding how the precast works, and in the temporary case, from a design point of view, what might be a shortfall of things that we should look out for. So we actually annotate that as actually information on the triangle with the number, and then associate that to a big sheets of health and safety information. Cool. So looking a bit more detail now, you see on the left, that's part of the kind of where the slab is, the raker coming in, and then the shoe on top of it is what's going to support the terrace precast units, and that's where the seating is going to be. So yeah, you just see the detail in it. That's it's worked through the whole collaborate process in the beam point of view of how us as the principal designer pushed our primary elements into a model that the fabricator from Laing O'Rourke's manufacturing facility can work to. They model every single individual bolt, even the shoes and the connection on top of it is all modeled in 3D. In a sense, the way of doing that is to make sure basically the building has been built already digitally. So when it comes to site, it really minimizes things that could go wrong in construction, and that also reduces health risk on sites. So that's kind of the main reason. And next slide. The roof is a big undertaking. Just to summarize it, on the top left, you see the image there. We got some really, really long mega truss. They span 170 meters. And instead of only looking at the permanent design cases, that is the first thing to do from design, we work with Laing O'Rourke to actually understanding how would the construction sequence looks like, because that's a massive truss. And based on, you see the 4 kind of temporary tower, we analyzed with Laing O'Rourke kind of how would that work. And not only that, the architects also got involved because when they position all the seatings, they've analyzed to make sure every single individual seats have line of sight to the mega screen at the bottom image there. So in order to make that height work, we also analyze when the tower is depropped. The truss will naturally deflect, and we get the stiffness just right so that when it deprop, it will locate in just the perfect position where the architects wanted. Concrete, that's complicated to say the least. So that's a good image. So you can see that's kind of like 2 precast panels. That's what called the twin walls. So this whole thing is manufactured in the facility from Laing O'Rourke's own facility called CEMCs, which I'll touch on later. And us as the primary designer, we actually go to the facility, understand how the precast works and how they pour the in-situ inside to connect with the joints and stuff like that. And based on that, you see the detail that provided in 2D there. We needed to design, say, not just the member itself, but the connections that actually fit into that whole ecosystem of manufacturing and fabrication that works with that capability. And also in the middle picture, you see every single rebar and the connections are all modeled in 3D. And that's actually the model that the on-site people use to fit everything together. Cool. Just a little bit more detail on that, just to show the complexity. So that's kind of like a sequence of how it's constructed, from the wall to finally how the slab actually goes into it. On the right-hand image, you can kind of see just how clustered it is. So if it would have been presented on site as a 2D image, it's very likely that some things might go astray, like it's actually touching the bars when you're not meant to, and that's when RFIs are going to come in. That's going to delay the whole process on site in the program-wise. And by having a 3D model, there's really no questions to ask on site. Very clear how it actually comes together, how it fits, and make sure everything is coordinated before it even come on site. And that's at the bottom is just how it actually looks. Precast columns, so as I said, almost all the concrete are precast elements. So we've gone through walls, we've gone through slabs, now a bit about the columns. So in the middle image, again, the 3D model, you see not only the rebar is modeled, even the couplers and the column shoes are modeled. So that, again, really minimize on-site. It's very clear how things fit together and minimize health and safety risk. Cool. On the precast models, that's just echoing on the detail side. From RIBA stage 4 onwards, we've actually gone to Laing O'Rourke's manufacturing facility to understand how things works and what do they need for us to provide that design information. So it's actually kind of like a bonus or like additional to our standard design that you would think of as a structural engineer. And we've increased from like 4 sheets, pretty much 2 sheets of details for standard details, all the way up to really, really packed 8-sheet details. And one of the lessons learned we can talk about in the Q&A is just we can even do even more. They can even more detail we can provide. But yeah, it's just kind of that collaboration of understanding from a design point of view, what do they need and what kind of questions would they actually ask, a problem they would come across. Precast model. So all these are the slabs that is the precast plank. So naturally, in a manufacturing, they can't just pour the whole thing. It got to be segmented. So we actually took on the role of using computational tools, mostly Grasshopper and BOM, to understand what the sizes of the panels they can cut, and based on the actual geometry of the slab, cut it into individual cases, then feed into the manufacturing systems. And not only that, on the right-hand side, that's in our Revit model. Just for an example of every single individual panels, you'll see all the data that is actually embedded in it. And all those, again, is talked through with the fabricator to understand what other information they need. Not only the primary bars, they may even be asking, like detailed stuff like setting out and stuff like that. And as a designer, there's no way we can put in that much information manually in the model and design for it. So those are all, you just cannot be done without a digital workflow to actually automate that process. A bit about CEMs. So that's the, I've mentioned earlier, Laing O'Rourke's Center of Excellence and Modern Construction with Explore, which is part of Laing O'Rourke, I believe. So Everton is actually their flagship project on going for this approach. Every single, the lattice slab, the precast plank, also the twin walls, and even all the facades, which is quite interesting. There was a slide on facade, but the facade, hopefully later in the future you'll join an Everton game and you can look at the facade there. All the bricks are very kind of like, how should I say, it's not standardized. It's kind of like moving out of place everywhere. Every single panels for the facade is precast and also created in the facility. And in the controlled environments, that's really why within the time frame we can make this happen with the manufacturer and contractor. So in the picture, that's one of the lattice slab. So interesting thing from the design point of view is we would have designed it differently if it's an in situ slab, because that's rebar embedded when it actually comes on site. And then that's additional rebar in the in situ. And again, all this, we can't design to it unless we actually understand how the precast elements works. Cool, just some final points. So on the left-hand side, that's kind of the architecture rendering. And on the right-hand side, that's the actual product. You can kind of see the kind of the brick facade that I mentioned earlier. So the building, I think one of the key points here, the first one, the building has been built digitally many times, which I've mentioned before. The key thing there is just really minimize surprises and danger that workers might encounter on site. Digitally enabled workflow between designer, fabricator, and contractor. Hopefully from the previous slide, you can kind of see how knowing the fabrication and the manufacturing actually affects our design as a structural engineer. And finally, explore digital tools to automate repetitive tasks whenever possible. So the example I've given is like the precast slabs. There's no way we can manually cut correctly that much panels and embed so much design information into it within the Revit model. So whenever you can get a chance, you can see like, oh, we can automate a process. Definitely explore that. Cool, that's me, thank you.